Hi, Professor. For our project, Hannah and I chose to study the Lotka-Volterra differential equations. We chose these equations because they felt comfortable to us. They felt like things that we had seen throughout the course. They're very common in any differential equations class, and we were able to learn how to define the systems as linear and first order after our coursework. And so after seeing that, we felt really good to start on this project. We saw direct parallels to the class. Just a brief introduction on the namesakes of the founders of this equation. Alfred Lotka was a actuary. He was a statistician who was interested in chemical decay and rates of decay within chemicals. Volterra was actually interested in ecology after learning about a fish species that was a predator that was showing up more and more in fishing lures. So what he observed was that there was a greater abundance of predators after a cease in fishing, and that observation prompted his inquiry into trying to model that mathematically. Interestingly enough, these two did not work on these equations together. They actually worked on them in parallel. Similar time frame, just in different places. They didn't collaborate at all. And so that's why they both get the credit. And, it's called the Lotka-Volterra equations. So to know about these equations, we know that it's a linear first order differential equation. And that it, at least in the case of Lotka, it was derived from the population or logistic growth equation and was expanded upon to include variables you'll see in the next slide. And lastly, these are not just used for applications in ecology, but any type of predator-prey interaction. And so while Volterra was primarily interested in accounting for why there was more predator fish after World War I and fishing had ceased, that's not necessarily the only application. Ecology is not the only place we'll see these.
Okay, so here we are shown the Lotka-Volterra equations. And on the left-hand side, we have the rate of change for population of the predators. And on the right, we have the rate of change population of the prey. So X stands for the predator population that we start off with, and Y is the prey population that we're given at the beginning. So there are 4 constants in this equation, in either equation. So alpha stands for the prey increase rate, meaning that the births of prey and so on. And then beta stands for the probability that the 2 species come together. So beta and delta are the same, stand for the same thing. So the interactions between the prey and the predator. And gamma stands for the predator decrease rate, meaning that their deaths.
So some of the assumptions of this model, the foremost is that prey is the limiting factor to predator population growth, meaning that if a predator species is left to its own devices in an idealized circumstance, they will reproduce, their population will grow exponentially until it reaches this carrying capacity, petering off at this asymptote. And it will eat, and it will not be sated, essentially. It will decimate the prey population. And that's something that Volterra had observed. So in the during World War I, there was a halting of fishing activities. And once the fishing resumed, fishermen were pulling up more and more predators. And the reason they were finding more predators in the ecosystem was that the predators had decimated the prey population. And as a result, they reproduced at this beginning exponential and then leveling off rate. And so while this equation is good at showing one observation that Volterra and his colleagues made, it doesn't account for some of the things that we see in reality. So species evolution, for example, is not included in the model, meaning that, say, a predator fish was somehow less competitive than a prey fish, that wouldn't be taken into account. Behavior and environment is also neglected. So adaptations and changing of a prey species is also not included in the model, which has drawn a lot of criticism because it is too simplistic in some ways to adequately represent what occurs. And so on the right, I just put a little image of an owl that's very well adapted to his habitat and ecosystem. He is doing mimicry and camouflage to avoid predation. And so that's something that hasn't been taken into account in the model.
Okay, so here we have done a general solution for the two equations. And so since this is it's a linear ordinary differential equation, we can solve this using the separation of variables method in order to solve the equation implicitly. So first we combine the two equations into a single differential equation, dy over dx. And from there, you can then separate the two variables, having the y on the left and the x on the right, having with dy and dx. So having the two variables on either side, you can then move the dx component onto the left side, setting the equation equal to 0. From there, we can find the integral of implicitly of each dy and dx, which will then give us the equation for population equaling delta x minus gamma ln x plus beta y minus alpha ln y. So our first case study that we went over was with the Hudson Bay Company, and this research was done from the year 1900 to 1920s. And the company had they retrieved animal pellets in Canada. So the animals that they primarily caught were Canadian lynxes and snowshoe hares. So with these populations, they noticed a correlation with their population, the change in over the course of each year. And they noticed that as the hare population increases, the lynx population would also increase, just a bit delayed. And if the hare population decreased, then the lynx population would decrease, also delayed. But with this information came some discrepancies with their data. They noticed that the equation could not be used with a small population since there would be external forces that would impact a smaller population too much, therefore making the data incorrect, such as like deaths, such as hunting of the animals that would impact the amount of predator or prey that will start off originally, or would make a deviation with the outcome with the data. Okay, so here are two graphs with the proportionality of each species. So you can see that the red line represents the hare population, and the blue line represents the lynx population. You can see as there's a spike in the hare population, the lynx population would also have a spike shortly afterwards. And you can see that there's they react proportionally to each other, which can be seen in either graph.
And so the second case study that we went over is somewhat outside of the scope of the class, but we felt it important to highlight that, again, these equations are not solely limited to the natural physical sciences, but also have applications in the social sciences. And so in 1967, an economist named Goodwin created this application for the Lotka-Volterra equations, in which he argued that workers were synonymous to prey species and capitalists or business owners were synonymous with a predator species, and that their interaction was analogous to that of the predator and prey species interactions that we would see more commonly with like the lynx and the hare. And so with this, Goodwin argued that there on the left-hand side of each equation, there is going to be some type of change with time. In the first equation, it's going to be change in employment rate. In the latter, it's going to be the change in labor share of total national income, meaning that that is the amount with which workers own the profits of a company or the output of a company. And that there is an inherent antagonism of the two. And so with that, we were able to see that not only do these two parties have conflict with one another, but that there are applications to the predator-prey species that we may not traditionally think of or may come to mind quickly. And so with that, we thank you for your time, and please ask us any questions if you have them via email.